frente aonde?
Okay, and then I'm also very happy to announce the next speaker. So that's Jesus Carlos da Mota from the Universidade Federal de Goiás. And he's talking about multiple traveling ways combustion for two-phase flow through a porous medium.
Thank you for the presentation. I would like to thank the organizer for this opportunity to talk here, Alexei and Marchesin. Okay. Our outline, the model is derived in one work, some years ago. I work with the Marchesin and another guy from UFG, UFMG University. I would like to talk about solutions like traveling waves. Traveling wave is an ODE system associated with the PDE system. I find some multiple traveling waves combustion for a particular case of the model. We call this particular case the immobile oil. The immobile oil is when the viscosity of the oil is very high. So the system is simplified, okay? Then we talk about multiple traveling waves combustion for the complete model, and at the end, some comments. Okay. The motivation for the model is gas combustion. A work of Chapman-Jouguet in the beginning of the last century, okay, and in situ combustion, okay, this work here, 1980. Okay. Here is the porous medium. The problem is one-dimensional. This is a picture of the porous media. The variables, unknown are S. S is the gas saturation, okay, a function of the space and time, the temperature, and a fraction of the burned gas. The fraction of burned gas is between 0 and 1. Here is a summary of the model. It is obtained from balance equations. This first one equation is the balance of the burned gas. This is the balance of the unburned gas. This is the balance of the oil. And this equation is balance of energy, Darcy law, and the state equations. This first term here involves a function. Q is the reaction rate. Okay. If we substitute this, if we substitute this Darcy law and the state equation in the other equations and add these three equations, we obtain our final system, this system, okay, where we integrate compressibility, volume, and pressure change due to the chemical reaction, a system of three equations. Here, F is the flux function of the gas. We work with this kind of function. Okay. Q is the reaction rate. We consider the reaction rate is truncate from some small temperature. Here we put theta 0. Okay, like main problem use this truncation as when they studied traveling waves, as Shivasinski in 2002, the function H here involves the capillary pressure. We only need that this function is negative in this work, okay? The other quantities involve the physical parameters as the average of densities, thermal capacities. Q is the heat released by the reaction, okay? If we solve these three equations using difference finite with this initial condition, this green line is the temperature. The temperature increases until the combustion temperature, and a traveling wave is formed. So then our problem here, we would like to prove that this traveling wave occurs. For our case, we prove mathematically that there are two temperatures that this traveling wave occurs. It's not expected physically, but mathematically we prove that we find two combustion temperatures. Okay. And works, and some works involving traveling waves. Combustion front is a traveling wave in this form, depending only on only one variables, saturation, temperature, and fraction of the burned gas. In our case, the traveling wave is from the left to the right. Okay, sigma is the speed of the front. Okay, the traveling wave connects a burned state, epsilon equal 1 when the state is burned, to the unburned state, epsilon equals 0. That is, we would like to find the traveling waves with this condition. When the parameter, when the variable C goes to minus infinity, the solution goes to the burned state, and plus infinite, the solution goes to the unburned state. Okay. If we substitute that traveling waves in the PDE system, we obtain this ODE system. Here we integrate to n time. A and B are constants of integration. Okay. Using these boundary conditions, this equation here is automatically satisfied. And if you use this condition here with the plus, okay, these two equations give us a relation involving the unburned state and the velocity of the front. This is the relation. It's a kind of Rankine-Gonyou condition, okay, involving the speed, the burned state, and the unburned state, with A and B are these constants. This relation, beta over alpha, is a value important in our analysis because the speed change of sign, if we take FO over SO, this is the FO over SO is the velocity of the particles ahead of the front, okay? So if this relation change, the velocity may be negative or positive. The case when FO over SO is less than beta over alpha was, the traveling wave was proved in this work some years ago, certo? Now, we are like to talk about this case. In this case, FO over SO bigger than this value, we found a multiple solution of the traveling waves, okay? This is the possible states of burned, the possible burned states, okay? That can be connected to the unburned state by a combustion wave, okay? This is in the space, this is in the plane. This plane when epsilon equal to 1, this is the possible. What we would like to find is some state here when epsilon equal 1 that can be connected to this state, to this unburned state by a combustion wave. Okay? So we have to solve that, to solve the ODE system and find orbit from an burned state to this unburned state, connecting this state, okay? Here we transform the interval of temperature theta 0, theta 1 to the interval 0, 1 to facilitate the analysis, okay? In these new variables, the system is this. Now we have to find orbit of this system, join this point to this point. This is the burned state. Now the temperature, when the burned state, the combustion temperature is that 1. So at the combustion temperature, T is equal 1, okay? And we like to find orbits from this point to this point. As epsilon needs to decrease, from 1 to 0, so epsilon point needs to be negative, okay? So it is to show that that one needs to be in this interval, okay, where C sub D is this point. As I said before, we like to find an orbit from this point, W1, to this point here, where the parameter of our system is just the combustion temperature, that one. When the temperature, that one, is near to theta 0, the orbits from here to here, the orbits enter W, the unburned state, tangent to this plane, sigma. So in the plane, the orbits from here enter this point tangent to this line. Here in the space, tangent to this plane. When the parameter is the combustion temperature. When the combustion temperature is high, this orb cross this plane. Okay, the orb from here cross this plane. So we don't have connection from this point to this point. So we expect that we have one temperature parameter that the orbit from here to here is just this orbit. Two reasons for choosing connection, strong connection. We call these orbits a strong connection from this point to this point. This orbit has a particularity. This orbit is this unstable manifold of this point joined with the stable manifold of this point. So we have this orbit here. This orbit here, the unstable manifold of this point. This is a center manifold joined with a center manifold of this point. So we call this orbit just a strong connection. Two regions to choose a strong connection and reject the other connection as non-physical. Here we have other connection, here we have a strong connection. Two regions, let me see. Numerical simulation of the PD system indicate that only combustion fronts correspond to a strong connection actually formed. In particular, different injection temperatures give rise to traveling waves with combustion temperature that is independent of the injection temperature, like this. If we inject different temperature, we obtain the same combustion temperature. Okay? The other region is physical. If this solution is a strong connection, then for n finite parameter here, this integral is finite because the temperature approaches zero exponentially. Thus, the total heat ahead of the combustion front is finite. This conclusion does not hold for connections that are not strong. So we consider only strong connection to solve the problem. Okay. The particular case for immobile oil, the saturation is frozen as a constant value here. And in such case, the other system reduced to this system, only temperature and the fraction of the burning gas. We like to find orbits from this point. This is this point corresponds to the burning state, to the unburned state here. And T1 is the parameter. So we have to change the parameter and obtain orbit of this system connecting these two points. Okay. Our result in this case is that there exist exactly two temperatures, T1 and T2, with T1 star in this interval and T2 star in this interval, such that the orbits corresponding these two parameters, leaving V1, enter the equilibrium V0 as a strong connection. That is, these orbits correspond to combustion waves. The existence of these two temperatures follows from the geometric singular perturbation theory. What we do is we can see that the orbits from this point leave this point just in this triangle. And the speed, now, and the declive of the orbit leaving this point increase from 1 to increase from 1. This picture is the slope of the orbit in this point. Okay, this slope increase from 1 to some value, constant value, and then decrease in this way. So the slope increase and then decrease. When the slope increase from 1, for the parameter near to theta O, the orbit is in this form. Enter this point tangent to this diagonal. This is not a good connection. We would like to find a connection of this form. When the parameter is the maximum point of this slope, we can prove that the orbit from here cross this line. So we don't have connection. So we expect to obtain one connection of this form. This is a good connection. Okay? But we have two intervals that's happen. Because this slope increase and then decrease. So, increase until here and then decrease until here again. Okay? So we find exactly, now we find at least two temperatures. In this case, we can prove that this is just the two possibilities. Okay? For this, we use the Melnikov integral to prove that there are exactly two temperatures. We construct, as usually, we construct the separation function of the stable and unstable manifold. So this is the separation function. Two functions for each interval, okay, for the parameter, and prove that this derivative of the separation function is negative in this value, that this is just that one of the temperature, of combustion temperature, and positive in the other. So we have just two combustion temperatures. Okay. For the complete model, we can't prove that there are only two temperatures, but we prove that there are two intervals of temperatures in this coil, two intervals, such that if that one is in this interval or in this interval, then the that one orbits leaving the burned state enter the unburned state as a strong connection. We don't prove unicity, but we prove there are two intervals that this happen. That is, this orbit corresponds to a combustion wave connection from here to here. The proof uses the case of immobile oil and certain invariant region in the space here. So we find two intervals of temperature here, two intervals that for temperature here or here, we have just a connection from here to here, a strong connection from here to here, from the burned to the unburned state. Okay? Let me see. Our comments. Traveling waves are obtained as strong orbits of an associated system connecting the burned to the unburned state. In case of high viscosity oil, we prove that the combustion occurs for exactly 2 temperatures. For the complete model, we find 2 distinct intervals of the combustion temperature. Numerical simulations indicate uniqueness of the combustion temperature as physically expected, but we don't prove this analytically. Here we have some reference of our work.